Thank you, and thank you for inviting me to present in this series. The work I'm going to be talking about is with Tilman Burgess, and it's very much preliminary and work in progress, as you'll see, and is more about a research agenda. We have a few results, but we're hoping to get more as we continue on this project. Okay, so this project is basically about similarity and learning in games, and it takes place in the context of a bunch of recent work where we've got now, I think, a much better understanding of the role of higher order beliefs in equilibrium play. And there's been a lot of work from Global Games and elsewhere just showing how important it is to understand what's happening with these higher order beliefs. But this raises the question about how people come to learn about these higher order beliefs when we're looking at equilibrium behavior. And I think it's reasonable to say that when we're thinking about equilibrium play, to the extent that we think of equilibrium as having any positive content, it's really coming from a perspective where we think of people learning how to play in equilibrium. So people are playing the same game over time, seeing what other people have done over time, and adapting their behavior to what they're learning. But if we're in an environment in which higher order beliefs are supposed to be playing an important role, that means we're talking about an environment in which people are getting some kind of signals that are giving them information about the sort of beliefs that the other players might have. And so if we have this environment with these signals that the players are supposed to be responding to, these signals that players are supposed to be making their behavior dependent upon, then this learning has to take into account that they're learning behavior over these signals. But there could be a lot of signals. And if we're learning about how people are playing in response to a particular signal, it seems reasonable to think that when they're doing this learning, they're not going to have precise knowledge of the signal, but they're going to instead be thinking about similar signals and the information that they're getting from these similar signals. And so with that as sort of the context, what we're doing in this project is taking seriously the idea that similarity is going to be important. So we're going to propose an equilibrium concept, which we call similarity equilibrium, for games in which people are going to be seeing bunches of signals, and they're going to treat some signals as similar to these other signals. And we're going to look at the relationship between this equilibrium concept and classical equilibrium concepts. And then we're going to investigate how people can learn when they have this similarity-based view of the world. And we're going to have a look at what convergence is going to imply about similarity equilibrium, and whether some equilibria are more likely to be reached than others. Okay, I've got these irritating menus up here, so just give me a second so I can get rid of that. And let me see if I can just minimize this thing here. Just give me 1 second. Hide video panel. Okay, that was not what I wanted to do. Okay, fine. I'll have to live with that thing up there. I can put it over there. Excellent. Good. All right. So what are we going to be doing? We're going to be looking at a project. The first important thing, in contrast to much of the existing work which has looked at similar kinds of questions, is we really want to treat these signals as being payoff irrelevant. So the role of these signals is only going to be to allow to generate correlations in the kinds of beliefs people have about what's happening in the game. It's not going to be directly payoff relevant. Here, because this is, I confess, early days in the project, we're going to be very bold and just take the notion of similarity as exogenous. We're not going to be able to explore where this notion of similarity came from. But importantly for us, we are going to allow for the similarity to be non-transitive. So while 0 is similar to 0.01 and 0.01 is similar to 0.02, 999.99 is similar to 1,000, but of course, 0 is not similar to 1,000. So we don't want to impose transitivity. We're also not going to impose symmetry. And the best example that we could come up with is Tilman's. Tilman loves his dog. So every dog that Tilman sees reminds Tilman of his dog. But his dog certainly does not remind Tilman of every other dog that he's ever seen. Okay, so this is a failure of symmetry.
Sorry, can I ask a short question?
Yes.
Signals have to be payoff relevant. You're not allowing for payoff relevant signals as well.
Correct.
And why is that?
Because we really
why is that
want
the important case?
Okay, but because as you'll see, the sort of results that we're going to get, this is really about whether people can learn to play things like sunspot equilibria. This is really about whether people can learn to play these equilibria where higher order beliefs are playing a role, where we have, if you recall back to the work of Bergman and Morris, they make this nice distinction between payoff relevant types and belief types. Okay, and so we really want to focus on the role of belief types in determining equilibrium play and whether players can actually be in an environment and learn about these belief types, or end up having behavior which looks like there are these belief types. Any other questions? Great. So what you're going to see in our results is that when similarity is symmetric and transitive, then similarity equilibria are just correlated equilibria. If similarity-based learning converges, we are going to get similarity equilibrium. So we've got the right notion of equilibrium in some sense. And then finally, what we're going to see is that it is in fact going to be very hard to learn things like sunspot equilibria and behavior where these payoff types are going to be relevant. So in this, I mean, this project really came from a feeling that a lot of these higher order belief arguments, while they're very elegant, also seem to be kind of fragile. And we're trying to get a handle on what is the source of this fragility. And this is one way to try to get a handle on that. Now, I should be very clear here. This is taking place in a very now growing and large literature where people are looking at similarity in learning. And there's just a subset of the papers there. Given that I only have an hour, I'm happy to talk about this literature in the discussion, but let me just go on and about the relation to the literature after you've seen what we've done. I never like roadmaps, but there it is. There is a roadmap. Okay, so let me just quickly launch in and give you a sense of what we're doing. We're going to look at a very simple setting. There's just going to be two players. There's going to be a finite set of actions, AI, for each player. As I said, payoffs are only going to depend upon behavior, not upon the signals. I'm going to denote by theta I, player I signal. And again, for simplicity, we're just going to restrict attention to a finite set of signals. F is going to be the joint probability distribution over pairs of signals. And every signal has strictly positive probability. But importantly, not every pair of signals has positive probability. As you'll see, we have some examples where some pairs of signals will have zero probability. So here's our basic notion that everything's going to be built on. We have a notion of similarity, which I'm denoting SI. So the notation theta hat I is in SI of theta I, just means that when player I sees theta hat I, he thinks of theta hat I as being similar to theta I. So this is going to be a similar, from this, we're going to get a correspondence, which associates with every state a non-empty subset of states. And we're going to assume a bunch of properties. One, which is going to be maintained throughout, is reflexivity. Every state the player thinks is similar to itself. Two others, which I've already alluded to, which we'll assume in the first proposition, but not thereafter. The first one is symmetry. If player I thinks that theta hat I is similar to theta I, then he thinks that theta I is similar to theta hat I. So in general, we will not assume that. Transitivity. If theta hat I is similar to theta I, and theta tilde I is similar to theta hat I, then theta tilde I is similar to theta I. Again, we won't be assuming that. I think these will become a little bit clearer as I go through some of the examples. All right, so here's our fundamental notion coming from the similarity correspondence. What's a similarity equilibrium? So it's just that each player is going to be choosing a best response to their behavior of the each player's behavior will be a best response to the behavior of the other players. We're going to restrict attention to pure strategies. So then I'm going to denote a strategy as sigma I. For each signal that they see, they can choose a pure action. So to the extent that we might want mixing in the background, we're going to be purifying using the theta I's. Now, these signals are path irrelevant. The only thing that players care about is what are the other players doing. So we've got player I, here is player K's behavior, sigma K of theta K. So we're going to be taking expected values over theta K, but you'll notice here there's an outer summation. The outer summation is I'm summing over all of those states that player I thinks is similar to theta I. So when player I sees the signal theta I, he's going to be, when he's forming his beliefs over what the other players are doing, he's treating it as if theta I, it could be theta I, or it could be theta hat I. So here I'm taking the expected values of payoffs over all of the theta Ks that could have arisen, and the theta hat I's, where each of those theta hat I's are similar to theta I. Now, just to one other quick comment, it's simpler here. This is not the conditional expected value because I didn't divide by the probability of the event of theta I, okay? But that just keeps the notation simple. Any questions on that? Okay, so that's our notion of a similarity equilibrium. If every player has a unique best response, then a similarity equilibrium, sorry, this is the assumption, not the proposition. I'm running ahead. So I want to assume unique best responses, and I'm going to give you an example later on showing why this is important, even for the simple result we're going to get. So for every player and for every state theta I, for every pure strategy of sigma K, player I is going to have a unique best response, okay? So with the similarity, it could be that player I thinks that there's some probability that the player K is choosing top, some probability that player K is choosing bottom. The similarity correspondence is going to allow for this sort of induced mixing behavior by player K. But that induced mixing behavior is not going to be so rich that at some point there'll be indifference. Is that clear?
Can I ask one question quickly?
Of course.
So for me, actually, it was a bit quick, this similarity equilibrium definition. So there's this F, which is a joint distribution, I guess, of types, is it?
Yep. Yeah,
and,
so F is the joint distribution over the types. So this is the probability that player I signal was theta hat I, player K signal was theta K. So this inner summation is giving me the unconditional expected payoff for player I from choosing the action AI when player I actually received the signal theta hat I. So if we didn't have any notion of similarity, we wouldn't have the external summation, and we would just be asking for each player, you should be maximizing your expected payoff, or equivalently, since I'm just talking about, I'm not asking values, I'm asking what's the optimizing behavior. What is the action that maximizes the unconditional expected payoff for each signal value? But now, because of this notion of similarity, when player I is choosing his action in this, when he sees the signal theta I, he actually can't distinguish between theta I and theta hat I. So he's going to put positive probability on the behavior that player K could be choosing for signal realizations that player K could get only when player I was seeing the signal theta hat I, not the signal theta I.
Okay, I get it. Yeah. So basically, just because there is dependence between theta I hat and theta K, that if there were independence, this would also not do anything.
Exactly. And this goes back to our original motivation. So we're thinking about these signals that the players are getting as being the modeling device that we use to provide a disciplined model of these higher order beliefs and how the beliefs of one player about the other player's beliefs are related to that player's beliefs about his beliefs.
Thank you.
Any other questions? Great. So when we have these unique best responses, each player's behavior in a similarity equilibrium is just going to be a correlated equilibrium. And that's not surprising, because that's all we're just doing is we can interpret now the induced behavior that comes from this symmetric and transitive correspondences as each player, when they get a signal, they have to be best responding to what the other players are doing. Since the correspondence is both symmetric and transitive, we're basically induced to partition over the signal space using the similarity correspondence. And so we're not getting anything interesting out of that. So now, that was a little bit quick, I think. So let me just go a little bit more slowly through several examples to illustrate what's going on.
Sorry, can I just ask a question about the previous slide about the
Sure.
assumption? So this is it's not an assumption on F. Why don't you need to make an assumption on F there in order to have?
So this is a joint assumption on F and the similarity correspondence.
Okay.
It's a joint assumption. And well, it's actually on three, right? It's on the payoffs, on the joint distribution, and on the similarity correspondence, right? And it's a generic assumption in the sense that there's a lot of finiteness in the world. So if you had a particular choice of the joint probability distribution, which given the payoffs and the similarity correspondence, we had an indifference, a small perturbation of the joint distribution will restore the uniqueness. Okay, so here's our first simple example. I've got a 2x2 game on the left. Player 1 chooses rows, player 2 chooses columns, and that's a asymmetric version of matching pennies. So there isn't a pure strategy equilibrium of this game. The signal structure is trivial. So this is a world in which, if we didn't have concerns about similarity, both players know exactly what theta is. Okay. And they know that the other player knows what that value of theta is. But we have similarity. And in this world, player 1 treats each signal realization as being distinct. Player 2, however, player 2 similarity correspondence is symmetric. When player 1 sees theta 1 or theta 2, he thinks they're similar to theta 1. And conversely, theta 2 is similar to theta 1, and theta 1 is similar to theta 2. But this is not transitive. Theta 1 is similar to theta 2. Theta 2 is similar to theta 3. But theta 3 is not similar to theta 1. Okay, so there is a failure of transitivity here. Here's a similarity equilibrium. Both players choose A in the first signal and the third signal, and choose B for the second signal. Now, player 1 clearly is playing a best response to player 2, because player 1 knows what treats all these signals as being distinct. Player 1 thinks that player 2 is choosing A in signal 1 and signal 3, and chooses A, and that is indeed a best response for player 1, as you can see. 1 is bigger than 0 in both cases. Player 2 is the interesting case, right? Now, what does player 2 want to do when he sees the signal sigma 2? When player 2 sees the signal sigma 2, theta 2, player 2 thinks that everything is similar to theta 2. So that given that specified strategy for player 1, player 2 assigns a probability 2/3 to A and 1/3 to B. But a probability of 2/3 on A, 1/3 on B makes B a best response. Okay, so this is a similarity equilibrium. The induced probability distribution on actions is now on the right. When it's theta 1 or theta 3, we're choosing A. When it's theta 2, we're choosing B. So it's 2/3 on AA, 1/3 on BB. But obviously, this is not a correlated equilibrium given those payoffs. Because if we recommend to player 2 to play B, player 2 from this putative correlated equilibrium infers that player 1 is going to play B, and so would want to deviate to play A. Okay, so this is an illustration that we can have a similarity equilibrium where the induced behavior is not going to be a correlated equilibrium, and the failure of that comes from the failure of transitivity of the similarity correspondence. Here's another example. Player 1 now has a choice of two actions, A and B. Player 2 has a choice of A, B, or C. Now there's only two private signals for the two players. Player 1's similarity correspondence, again, is degenerate. He treats each signal as being unique and distinct. Player 2, on the other hand, when he sees theta 1, he knows that's a distinct world. But when he sees theta 2, he thinks there's nothing special. It's just like theta 1. So this is transitive. There's not a lot to do when you only have two states for each of two signals for each of the players, but it's not symmetric. When player 2 sees theta 2, he thinks that theta 2 is similar to theta 1. But when he sees theta 1, he does not think that theta 2 is similar to theta 1. So that is not symmetric. Here's a similarity equilibrium. So again, the interesting player to focus on is player 2. The players are playing A in the first signal and B in the second signal. So is player 2 going to be willing to play B in the second signal? Well, when he sees the second signal, he doesn't think there's anything special about theta 2. So his inferred distribution over the behavior of player 1 assigns probability 1/2 to A and 1/2 to B. Well, if he sees 1/2 on A, 1/2 on B, B is a much better strategy than either A or C. And so indeed, for player 2, playing B is a best response to this particular similarity correspondence and specified behavior. And so there is the implied distribution over behavior. Again, because of the degenerate structure of signals, the players coordinate on A with probability 1/2 and coordinate on B with a probability 1/2. But again, this will not be a correlated equilibrium, because again, when player 2 is recommended to play B, he infers that player 1 is going to play B. And if he knows that player 1 is going to play B, he would rather play C. Again, this was a similarity equilibrium only because when player 1 saw the signal theta 2, he doesn't think there's anything special about theta 2. So it's as if it could have been theta 1 or it could have been theta 2. So then he believes there's a 50-50 probability on A and B from player 1. And so then he strictly prefers to play B. So similarity equilibria are quite different from correlated equilibria. Here's the final example to show why we needed to have this unique best response in the proposition. So now we do have matching pennies as being the underlying game. Now I'm looking at a world in which nobody thinks that these signals are special at all. So this is a game in which we do fail the unique best response. No matter what, there's a specification of strategies for player 2, such as heads after theta 1, tails after theta 2. Then from player 1's perspective, he believes he's facing a 50-50 randomization over heads and tails. That's what the typical purification of the mixed strategy equilibrium would ask us to do. And heads and tails are both best responses. But that means that there is the mixed, alleged purification, right? Heads after the first signal, tails after the second signal. But because of this correlation structure in the signals, we don't have a correlated equilibrium. Okay? So what I've done so far is basically introduce this simple notion of a similarity correspondence and the associated notion of similarity equilibrium, and give you several examples that show that when the similarity correspondence fails to be transitive or symmetric, or we don't have unique best replies, that we won't get a correlated equilibrium. Now, the real question that we're interested in is what sort of behavior can we learn? So let's think about that. So now I'm going to think about a world in which time is infinite. In each period, there's going to be an IID realization of this private signal, theta 1t for player 1, theta 2t for player 2. After each signal realization, each player is going to choose their action, A1t and A2t. And at the moment, I'm going to look at the case of perfect memory. I'll look at the bounded memory case afterwards. In the perfect memory case, both agents are going to see the entire history of their own private signals. They never see the private signal of their opponent. They see the history of past actions of their opponent. And of course, they remember their own past actions. And players are going to have perfect memory. How are we going to do learning? Well, in every period t, each player I is going to observe the realization of the signal theta it. When they're going to form their estimate of how their opponent has played, they're going to look at every past period in which their signal theta I tau was similar to the current signal that they saw theta it, because those are the periods which player I thinks is relevant, because he thinks, given that I saw theta it, he's thinking that all these other signals, theta I tau, which are in that set, SI theta it, these are all the ones that are similar. So these are all the ones that are providing information about how player K is behaving. And then player I is going to best respond to the frequency distribution of the other players' actions in those periods. So we're looking at a myopic best reply dynamic where we're updating beliefs according to the empirical distribution over past play. So far that's completely standard. The part that the bit that's different is that we're using similarity to determine how we're calculating that empirical frequency. Good. So we're interested in what's happening over time asymptotically. So we're going to be looking at those outcomes where there's an initial history, so that for each player and for every possible signal realization theta I, there was at least one period in which the player saw a signal that was similar to theta I. Okay, so that's just to get things started, because if I haven't seen anything relevant, then I have no way to calculate the empirical distribution. That's just a way to initialize the learning process. And of course, with probability 1, given our IID process, eventually there will be every signal is going to be realized. I'm going to say that a history is admissible if the first T0 periods of some history agree with HT0. Learning is going to start after we have that initial history. So I don't really care what happened in the initial history, because I'm going to be looking at asymptotics. Now, let's suppose I take some arbitrary history HT, which is going to be admissible. So it's going to be including stuff that happened after our initialization history. The set of possible continuations that would be associated with that history, well, that's going to be the set of all possible outcomes, H hat, infinite sequences of state realizations for player 1, state realizations for player 2, and actions for player 1 and actions for player 2, such that the projection of that outcome onto the first T periods is precisely HT. So it's just the set of continuations. So the myopic learning process that I've described is going to induce a probability measure over these continuations. And I'm interested in what this learning process is going to imply. All right, so here's our first easy proposition. Let's suppose I have some admissible finite history. So I'm looking at some history with the property that our agent is able to calculate the empirical frequencies because the there was an initial segment where every similarity, every state had an action associated with it. Now, let's suppose that eventually behavior is constant. And by that, I mean, for each future realization of the same value of the signal, we're choosing the same action. So if there is some time t, so that behavior settles down, with probability 1 under the induced measure from that history ht, then that behavior must be a similarity equilibrium. Now, this is very intuitive. In order for an event to have probability 1 under this admissible history, it has to be the case that the empirical frequency of the joint realizations of these private signals equals the population frequency. If behavior is settled down and is eventually constant signal by signal, that means that the empirical frequency of behavior over those signals replicates sigma. And so that now when the players are myopically best responding, they're not just best responding to the empirical frequency of past behavior, they're actually best responding in a similarity sense to the sigma of the other player. But that's a similarity equilibrium. Now,
Sorry, can I ask?
Yes, of course.
About on the previous slide about agreeing and to continue. You said it's a probability measure on the set of continuations.
Yeah.
But this excludes the possibility.
Oh, you've muted yourself, Eric.
So
you're back.
So I mean, I don't know the actual history. I only know this similarity classes to which, or the sim. Or do no, sorry, remember, no, I do observe. No, sorry, I do observe. Okay. I don't. Yeah, sorry, forgot. I was slipping into another theory.
No. Okay, but let me just expand on what Eric was getting at. What's important for us is that we're very much interested in the case where the similarity classes aren't symmetric. So what the players know, they actually know the true sequence of their own past signals, but then when they calculate their empirical averages, sometimes they're going to be pulling in actions that were chosen at different signals, right? Okay, good. Any other questions? Great. Okay, so now, but of course, you know, this sufficient condition is incredibly strong because we're saying that behavior settles down eventually. So it's eventually constant. And there's a lot of randomness underlying in the world. So that seems a little optimistic. So now let's ask for a slightly weaker condition. I do want to ask a little bit more from my setting. I'm going to ask for unique best responses. Now, for all admissible finite histories and any delta, any strictly positive delta, there's going to be some time t of delta, such that if there is a strategy profile, sigma 1, sigma 2, where from the periods t plus 1 to t plus delta, play is constant, signal by signal. If that probability is greater than delta, then we have a similarity equilibrium. Okay? So what's going on here? Well, the first thing to note is that I've got unique best responses. So that means that when a player is calculating his myopic best response, in order to hit a particular best response, I don't need to get the beliefs exactly right. It's enough for the beliefs to be in a neighborhood of what the other guys are doing. Now, the other critical thing is that if behavior is constant signal by signal for a long period of time. Now, remember that in this sequence, as I'm moving along, I'm getting new realizations of the signals. So my empirical frequencies of what my opponent is doing is going to be fluctuating. Nonetheless, the behavior is not changing. So that means that I'm choosing a best response to different beliefs. If it turns out that those different beliefs that I'm best responding to have the property that the behavior that I'm best responding to, has the property that the similarity expectation of sigma 2 is in the convex hull of those beliefs, then I'm also best responding to that because expectations are linear. And if I make this T delta large enough, there's enough variation in the realization of these thetas that with high probability, the similarity expectation of sigma k will be in that convex hull. And so that's what I need in order to get a similarity equilibrium. Any questions on that? Okay. All right. And again, though, I still want to, and this will come even clearer in a few minutes, these sufficient conditions are pretty strong, okay? I'm not at all giving you a theorem that says we should typically expect to see convergence of the learning process. Now let's think about a learning model in which there's bounded memory. So now I want to think about a world in which people don't remember the entire histories. So in every period t, each player I is going to observe, as before, their private signal theta it. They're now going to look at the last n periods in which there was a signal that they think of as being similar to theta it. So it's as if for each possible realization of theta I, they've got a memory bank that has n slots in it. And each time they get a new observation, they're going to put that observation into one or more than one of these slots, because a particular signal realization could be similar to more than itself. It could be similar, in the non-trivial cases, to some other signal. So they're going to put them into those slots, but they've only got n slots in each one. And then the players are going to best respond to the frequency distribution of the other players' actions in those periods. Okay. As before, we need to initialize it with an initial history. And so now I'm just going to be a little bit more demanding of this initial history. I'm going to ask that for each of my signals, they should have seen n past periods with information about that signal or a similar signal that they had observed. Okay? Is that clear? Okay. So we could first ask, similar to the previous case, well, what would happen if eventually play settles down, if play is constant? Now the learning process is noisier because it's only paying attention to the last n relevant periods. Again, we do get a similarity equilibrium, but now this illustrates just how demanding this condition is. Not only must that strategy profile be a similarity equilibrium, but in fact, it's got to be an ex post equilibrium. And by that, I mean, for any pair of signal realizations, theta 1 and theta 2, in the support of the probability distribution F, the induced behavior has to be a pure strategy equilibrium.
Can I ask something?
Yes.
So that means some of the examples you gave wouldn't satisfy this, right? As
Correct.
far as I remember. Okay.
Correct. Exactly. So that's saying that in fact, none of the examples that we had talked about so far would satisfy this. So that sort of behavior could not, if this is our criterion for whether we learn something or not, then none of those equilibria could be learned. That's exactly correct. Yep. Now, and the proof of this is kind of, I mean, it's almost, I'm not quite sure I should call it a proof rather than an observation, which is fix some pair of signals, theta 1, theta 2, in the support of the distribution of signals. after any finite history, at some future date, with probability 1, player 1 will have observed theta 1 in each period. Player 2 will have observed theta 2 in each period. Now, if n is large, that may be low probability, but it is positive, which means that almost surely that will eventually happen. But because I'm best responding to the last n periods, I have to be responding to the behavior of player 2, if I'm player 1, to player 2's choice in theta 2. Okay? So, again, this is very demanding. So let's ask for something a little bit weaker. Fix n. It may be 1. It may be that the players are only able to keep track of the last similar period. N is equal to 1. N may be equal to 1,000,000. Whatever the value of n is, there is going to be some value of delta n greater than 0, and sometime Tn, such that if we have a strategy profile and an admissible history, such that a similar property that we had before, we're constant on that long segment from period t plus 1 to t plus Tn, if that probability is at least delta n, then sigma 1, sigma 2 is a similarity equilibrium. Okay? So this is very similar to the result that we had before. The proofs is similar, okay? But notice now, the earlier proposition when we had perfect memory, it was a for all delta. Delta could be small as long as it was strictly positive. In the earlier result, in the background was the observation that since I'm looking at the entire sequence, it's enough to know that the empirical frequencies are eventually going to be almost right. That's not true here. Since I'm fixing n, and I've got these new random draws of the thetas, there's no guarantee at all that in any n period draw that the empirical frequency of the thetas looks anything like the population frequency. Indeed, if n is small, it may be impossible to get the empirical frequency to look anything like the population frequency. But the comment that I made earlier on still applies here. If you are choosing a best reply to two different beliefs, then you must be choosing the same action must be a best reply to any convex combination of those beliefs. So if I have a long sequence, t plus 1 up to t plus n, where I'm always choosing the same action given my signal realization as a best response, even though my beliefs of the opponent's play is wandering around in response to the different signal realizations that the other player might have observed, then I'm choosing a best response to the average. Okay? But now I need delta n potentially to be very large, because I want delta n to be large and Tn to be large to know that these wandering around beliefs have enough variation that my target belief is in the convex hull of those beliefs. Okay? The other thing to note about this proposition is that it doesn't say anything concrete about delta n and Tn. I've been saying that delta n, we want large and Tn to be large to get this variation. But at the same time, intuitively, the smaller that n is, the larger I need delta n to be. Right? Think back to the earlier proposition with perfect memory. If n is very large, then with high probability, the empirical frequency of my signal realizations will be close to the population. And so I can use some of those arguments. When n is small, that's not true. And as we saw from the previous proposition, when I had probability 1s everywhere, if delta n is getting close to 1, which we intuitively need when n is small, we're not just getting the similarity equilibrium, we're going to be getting an ex post equilibrium. Good. So that was all telling us that, I view this to some extent just as sort of proof of concept stuff, that the learning and the notion of equilibrium, that there isn't too much tension between the two. Now let's think about similarity-based learning and equilibrium selection. This goes back to my motivation at the beginning of the talk. So here I've got a game, and this is the results here hold for games in this class. We're thinking about games which have multiple strict equilibria, such as A, and B. This particular game is a version of chicken. And when you look at this game, there's an obvious correlated equilibrium that you would like the players to learn how to play, right? They would like to put positive probability in BB, as much probability as possible. But BB is not a pure strategy Nash equilibrium. The only way you can induce players to play B is if they put enough probability on A of the opponent. At the same time, you want to minimize the probability on BA. Okay, so you want to maximize the probability on AB. I may have misspoken, said BB, I meant AB. You want to maximize the probability on AB. You want to minimize the probability on BA. Okay, and so this is the kind of example that Alman points to as why we should be thinking about correlated equilibrium. And relative to my earlier introduction, of course, correlated equilibrium is a way of modeling behavior where, for some reason, outside of the game that we've written down, there is some mechanism that allows the players to correlate their behavior, which what we could interpret as saying that these higher order beliefs are playing a role. And so the question is, if players are playing this kind of game, can they learn to play this kind of game given the kind of environment that we're in? Okay. Now, so far, I was just abstractly, I was talking about the similarity correspondence, putting very little structure. And the examples of the similarity notions that I put down sort of captured that. I'm now going to put a little bit of structure on here, and it's just enough so that contagion-like things can kind of happen. So I'm going to make two assumptions about my similarity correspondence and how it relates to the distribution of signals for players 1 and 2. The first assumption is going to be one that will break synchronicity in behavior, right? If you remember those earlier examples where we had only probability on the main diagonal, that sort of means that whenever player 1 sees a particular signal, player 2 sees a version of the same signal, and so on. I want to break that synchronicity. And the way I'm going to do that is saying that for some player, there's going to be two values of the signal, theta hat I and theta I, with the property that theta hat I is not similar to theta I. So when player I sees signal theta hat I, he does not think that it's similar to theta I. He thinks theta I is different. And yet these two signal profiles both have positive probability. I'm now going to say that a signal profile theta 1, theta 2 is connected to another signal profile theta hat 1, theta hat 2, and I'll denote that with an arrow, if both of these signal profiles have strictly positive probability, and yet, no, I don't know why I said yet, and for each player, when player I sees their signal theta hat I, they think it's similar to theta I. Okay, so that means that when the players signal pair realized of theta hat 1, theta hat 2, each player is putting positive probability on the behavior of the other player in theta 1 and theta 2. Okay, so that means they're in the hat signal realization. What they think is happening in the non-hat signal realization is going to influence their behavior. And I'm going to assume that for every positive probability realization of the pairs of signals, for every player, and for each player, choose a different signal, I can construct a positive, what I'm going to call a positive probability similarity path from the first profile to the second profile. Okay, so again, what that is saying is that take two distinct signal profiles, both of which have positive probability. There is going to be a positive probability similarity path that takes me from the first one to the second one. So that means that the behavior on the first one, through this indirect chain of these similarity-related signal realizations, is going to potentially influence the beliefs of the player at the last signal realization. Is that clear? Okay, now, this assumption, the first assumption and the second assumption are doing two different things. The second assumption is guaranteeing that what a player could think is happening at one place is relevant in the other. But that by itself doesn't break the asynchronicity, the synchronicity. We need the first assumption to make sure that that's going to influence behavior. Once we have those two assumptions, then we're going to get the result that we do get convergence, and in particular, eventually either people always play A or they always play B. Okay, so again, what we're going to get out of this is that asymptotically, either people are always playing A or players are always playing B. We can't get conversion to that correlated equilibrium. And so, in particular, we can't get conversions to this correlated equilibrium here. And we still need to make this precise, but we have a strong intuition that this argument holds not just for the strong assumptions that are made in terms of those assumptions, but we can weaken those a little bit, but we're still, sorry, let me rephrase that. The assumptions that we made to get this result, we think of as being rather mild in the sense that it'll hold for most of the similarity structures, but we need to make that precise. Okay, and that's my last slide. So let's have a discussion.